Good afternoon, everyone. It's pleasure to have Professor Sydney A. Barnes, faculty at Leibniz Institute of Astrophysics, Potsdam, Germany. And he has been doing professional astronomy there, and it's a good opportunity because that's why students are also here to listen him today, and it coincides with the ATSOA workshop. And he completed his Ph.D. In astronomy from Yale University 1998. And after that, he occupied positions at various institutes in USA and Europe. And right now, he is presently at this particular institute. And he works on cool stars and using the magnetic field and sun spot positions, he tries to find age of these stars, and that's what he would be speaking today. And in fact, he has been a prolific observational astronomer, particularly optical astronomers of, particularly stars in stellar field. And he has observed from several telescopes. I hope he will share some of the experiences with us. And one minor planet, I think 28018, has been named after him. And he has guided several postdoc and PhD students. He has several honors to him. And we very much welcome Professor Barnes. And we are ready to listen you. And your lecture, please.
Thank you, Brijesh, for the introduction. Thank you all for spending an hour of your time listening to me. I'm going to talk about this thing called gyrochronology. It's so I should explain first of all what this thing is. It comes. It's a neologism I cooked up in 2003, so it's about 20 years old. And it comes from the Greek. Gyros means rotation. Chronos means age, time. And logia, logos means study. So it's the study of ages using rotation. Before I get too far along, I want to acknowledge takes a little while, I guess, to do the display. Right here. It'll automatically find this. Okay, good. Play. Good. Everything works. Well, let's not go too far ahead. No, this one. Oops. The first desktop. One full screen. Okay, we're back on track. That's good. Don't fiddle any further. When a thing works, it's done. So I just want to start with a few acknowledgements, so you know on whose back I'm standing. Family and friends, students, postdocs, and collaborators for suffering. A lot of what I do is incredibly boring, and it's amazing that people continue to work with me. There are other colleagues, both helpful and oppositional. Both, of course, help. The German taxpayer, for what my wife calls the European vacation we could not otherwise afford. And Aries, both science and non-science staff for the hospitality. So here's my little group over there. That's my boss, Klaus Strassmayer, okay, who built the Pepsi spectrograph, for instance. That's Jörg Weingrill, who has worked with me for over a decade now. He's now on the permanent staff at AIP. Dario Frijevski, some of the work I'll show is his. He was my PhD student. He's now working with Connie Arts in Leuven. Elizabeth Cole-Kodikara has been with me for the past few years and is headed to Australia to work with Mark Krumholtz there on star formation. David Gruner, whose most recent work that I'll present is his. And Ozgun, who's just started working with me. He's jointly advised by me and Klaus. Just to give you an idea of what the place looks like, that's the Humboldt House at the AIP. That's my window over there. That's me at my desk working away. Very nice old building that's a little over 100 years old. And there's a lot of ivy. And this kind of weather is sort of typical for Germany. And unfortunately, that's how it is for a lot of the year. The most scary thing about walking out of the building is every day when I'm going home, I have to face this guy. And that's Alexander von Humboldt. And you have to think every time you face his picture, his statue over there, what you did for the day. So that's quite a task to have to do every day. Where is the AIP located? So the building I showed you is this one over here with the 3 domes. The domes house telescopes, but they're not in use for research, obviously. Where AIP is written is actually the site of a new building that's almost finished at this time. And this area of Potsdam is called Babelsberg. Some of you may remember the film studios where Das Boot was filmed, for instance. That's Babelsberg Studios. So that's this part. It's in Eastern Germany. All of this is Eastern Germany, except that there was Berlin, right? Berlin was an island of the West in the East. And those of you who have seen the movie The Spy Bridge, the Bridge of Spies, that's the bridge. 2 different colors over here to the bridge, if you can see. This one is US Army green, and that one is Russian Army green. So that's right there in the middle is where the spies were exchanged. In fact, one day I was riding home from work, and the bridge was closed because they were shooting the movie. So it's that kind of place. There's a lot of water. This is the Havel River that flows through Potsdam. It's sort of a confused river because every river is dammed so much in Germany that the river doesn't know which way it's flowing. That's how it is. But a lot of the water, you know, these are lakes also that the river flows through. And the reason why you have so many of these lakes around is because this area of Germany was the terminal moraine during the glacial period. So there's a lot of sand over here because it's a terminal moraine. One other thing I should tell you that's pretty scary is that a bunch of people were killed trying to swim across in the bad old days over there and also over there. And so they were just shot by East German guards. So it gives you a kind of sense of the drama of the place. A little bit about the Leibniz Institute, maybe in order. It was founded in 1700 by Leibniz, whose notation you use for calculus. Then it was refounded about 200 years ago by Alexander von Humboldt, who gave these lectures and so sort of endowed the place at that time. And then there are a few discoveries There are listed Neptune, 1846, and so on and so forth. Radial velocities of stars for those who care about it. And some people may care about the black hole solution. Was Schwarzschild, Karl Schwarzschild, that this was. His son, of course, had to leave Germany because of the fascists. And Einstein too left around that time. In the 1900, Grotrian worked on the solar corona. So those of you who use Grotrian diagrams may remember that name. I stop about 100 years ago because then it's not history. The telescopes, this small set of 1.2 meter robotic telescopes is the one that I tend to use a lot of. We're currently working at the Institute on this thing, the 4 meter foremost telescope, which will have a lot of fibers on this thing, taking spectra of stars. I occasionally use this. In fact, just before coming here, I submitted a proposal for more time on the LBT for the next year. That sort of gives you the scale of what these telescopes look like. Those are people over there. We're also currently building an instrument, maybe two, for this beast called the ELT. That's already under construction in Chile. And so eventually we'll have some. This will be constructed after I retire, so I guess I shouldn't even bother, but it may be relevant for the younger people over here. Okay, now at last that's done with the prologue. Now the main talk. The ages of stars. Why do we care about ages? Just imagine that someone gives you a pile of your family pictures, right? I mean, you just get a whole pile of them, and you're trying to figure out what is the story of this family? What happened, you know? So then you look at each picture, and you look at each individual in those pictures, and you try to guess what age those individuals were. Once you do that, you can place all of those in a sequence, one after the other, and then you can read those pictures in the correct sequence and tell history. So before that, everything is just an event in science. It's only when you place them in a sequence that you can construct histories and chronologies. That's why we care about ages. Okay? So for instance, the set of histories, which has all of you sitting here in this room at this moment, is the only set of possible histories that's correct. If someone takes a picture, that sort of specifies that you are here for this event. What I'm talking about really is the galaxy. These are just objects in this galaxy. They're the stars. And we're trying to place the galaxy in context, how various pieces of the galaxy were formed. The first place I came into contact with ages was actually in this place, which is Grand Canyon, where I was fortunate to work nearby in a town called Flagstaff at an observatory called Lowell Observatory, which is just 100 kilometers from this place. And you can hike out here, you can go down here, you can even see the trail descending. This is one of the major trails in Grand Canyon. But one of the wonderful places to go is in front of this rock called O'Neill Butte, and go look over there, drink a beer, and go look at the river. But after a while, you start wondering what the ages of those rocks are. And in fact, in science, we first had to confront ages in a geological context. And then the story was that these things are timeless. In fact, the first big theory was that of uniformitarianism. And when James Hutton wrote his theory of the Earth in 1788, he came up with this conclusion that there was no vestige of a beginning and no prospect of an end. Things happened very, very slowly. This had a tremendous influence on Darwin, of course, in creating his theory of the origin of species, because it gave Darwin a lot of time, millions and millions of years, in order to create new species. So that's the idea that we're dealing with. Of course, in geology later, catastrophism also took a position, and we know that there are catastrophic things that happen in the world. Little bits and pieces of the rocks around here fall off. Sometimes you can have an earthquake, and you can dam a river, and you can do all those things. So nature consists both of uniformitarian processes as well as catastrophic processes. So that's a complexity that arose later. And now the introduction. So let's go forward by going back. Sometimes you just have to think, okay, what are we talking about? Let's start from the very beginning. Age is typically not a concern in fundamental physics, right? Most of you probably never had to take a physics class where they asked you, what's the age of this, what's the age of that? I mean, it doesn't make sense to talk about the age of an electron, right? It's specified by these few quantum numbers, and that's it. What do you care? Because every electron is identical to another. So it's really a property of macroscopic systems. And the only place, and correspondingly, the only place where you see some talk about ages is in entropy and thermodynamics. And then, of course, later, if you study about complex systems, you'll come across the various processes in there. It's a basic ingredient in constructing histories. And in astrophysics, especially in our galaxy, where objects don't come labeled with a redshift, and so we don't know how old they are, the ages of stars constitute the ticks of the abstract cosmic clock that orders things in time. So what is the age of something? I could have made it a question and so on, but there's no time for that. So I'll just tell you the answer. It's the difference in time between the present and its birth, measured using a suitable clock, right? The birth and the present. You just subtract the two, you get the age. Well, I haven't told you anything because I haven't told you what a clock is. Can someone tell me what a clock is? Throw out a wild answer. No? Yeah. A clock is a measurable variable V that changes systematically with time. So you'd represent it mathematically in this way. V equals V of the time, the age, and a few other variables, perhaps. The simple ones have those absent, okay? No X, Y, Z, and so on. Becomes all quite simple. And the age T, of course, can be obtained by inversion, provided you do all these measurements correctly. Or if you're doing it, or if you have a theoretical bent, of course, you want to make sure that the Hessian has certain properties, that's invertible, blah, blah, blah. All things happen that way. So the key point is to write T as a function of your variable V, which you can measure, and these X, Y, Zs, which hopefully you can also measure. So once you put all those things in there, you automatically have your T. But you have to construct this clock. And that's what is the problem, typically in astronomy. Okay? One note is that time and age are used interchangeably in my talk, because the age, of course, is just T2 minus T1. It's just a subtraction of these things. So here's an example of a clock. Here's a piece of a tree. There's a bristlecone pine that from the White Mountains of California. If you drive up the east side of the Sierras, you can go wander in there in this forest of the oldest trees on the planet. Some of them are 5,000 years old. Okay? Here's a cut of such a tree. You wouldn't dare to cut a tree like that today. You end up in jail. But this particular tree was at the BC AD boundary. Okay? This is 2,000 years ago. And then it keeps going back. There are the rings, right? Going back to 2500 BC. This is the time of the pyramids and the age of the Harappan civilization. And in fact, all through the American Southwest, if you find a little piece of wood you can set it up, you can study that piece of wood, match it up to a sequence using these trees, and go back 20,000 years to tell the age of when that particular hut or dwelling was constructed. That's how you tell the ages of those things, using these trees. So this clock, the number of rings, T, is specified by the number of rings. So each particular ring tells you when this thing was done. A fish. You have quite a few Bengalis here. I'm sure they like fish. All you do is take a scale of your fish and look at it, and then you can see the various growth rings, right? But a better way actually is to reach into the head of the fish and pull out this bone from the inner ear and study this. And so there's this particular fish that grew off the seamounts of New Zealand. And when scientists studied them, they were absolutely shocked because they were being fished out and served on tables in New York and elsewhere in the world. They ended up being about 200 years old. So it's like going to the zoo and eating the turtle over there, or the tortoise. Anyhow, so the New Zealand government has this protocol now for how to determine the ages of the fish. And this is like a 200-page document on how to do that correctly. And every time your batch of fish comes in, there's a sampling, and some of those fishes, the ages are determined to see whether it's okay to eat them. I mean, a big reason to go to Bangalore, of course, is to go to the IIA for those of us who are astronomers. But another very good reason actually is to just go and stand on this rock over here. This is, of course, the craton of which India is made, Peninsular India. Peninsular Gneiss, in fact, is the name of this rock, and it's more than 3 billion years old. You can just show up at Lal Bagh and wander around this rock. It's a pretty amazing thing. And of course, this piece of zircon is arguably the oldest piece of the Earth's crust. These zircons travel through the crust, of course. They get recycled, but they're so refractory that they put on a new layer as they go past. And a piece of this is actually more than 4 billion years old. Okay? There's a wonderful book, by the way, to read. Pranay Lal's book from 2016. That's where I found this stuff. How do we know the age of the sun? We know it from the rocks. And this is the gentleman who first found out a reasonable age for the sun. This is Claire Patterson sweeping his lab at Caltech. And the paper is this one, 1956, Age of Meteorites and the Earth. Okay? And he measured it from this rock that fell outside Flagstaff. You can go and visit this hole in the ground. This rock fell about 50,000 years old, 50,000 years ago. But the rock itself was measured, and it turns out to be 4.55 billion years old. And subsequent measurements have shown that that's essentially correct. By the way, that wasn't all that this guy did, because he's cleaning his lab over here for a very particular reason. It was contaminated with lead, and that made the measurements quite hard to do. There was a lot of contamination. And he realized that the lead was coming from the fuel that was in cars, the gasoline. There was tetraethyl lead that was added in there to prevent the engines from knocking, right? They go tuck, 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 tuck. You don't want that, of course. And the way they figured out not to do that was add this thing. Well, Claire Patterson realized that this was causing health problems. And of course, as soon as he did that, the oil companies tried to get him fired. To their credit, Caltech said no. He stays. In fact, he went on to lobby in Congress and get an addition to the Clean Air Act. And that's why billions of us are not poisoned with lead. So scientists do pretty amazing things sometimes. Ages of star clusters. All of you know this, right? I mean, master's students, I mean, you know that Sandage cooked up this diagram where if you plot the brightnesses of stars against colors, and you move those sequences for the open clusters all onto the same line, which means move them to the same distance, right? 10 parsecs if you want the absolute magnitude, then all of them form this kind of pattern where the youngest stars define what's called the main sequence. right? Then the more massive stars slowly peel off this main sequence, so that successively older clusters peel off further and further. And finally, you have a cluster called M67, which you can see with certainly with that little telescope you have out there. And that's about 4 billion years old. So the essential thing is that you can use the morphology of stars in this diagram to tell its age, right? So provided you know the distance of a star, you can place it on this diagram and try to tell its age, okay? That's become considerably easier since the Gaia satellite. But actually, even if you know the distance for a low mass star, it's going to end up on this line. So there's no hope, actually, of telling the age of a star, of a cool star, from an isochrone. And so you need another method. There's some details over here of sandage and so on, which I'll just skip over. Now, this is where rotation comes in. So if you look in the color magnitude diagram, which for a theorist is, of course, the luminosity against the effective temperature. For the observer, it's magnitude versus color. And there you have the track of the sun, for instance, starting somewhere here. It descends, the pre-main sequence comes here and moves here onto the main sequence. And all through its main sequence lifetime, that's all it does. It barely moves in position, right? The main sequence. Okay, well, let's look at what it does in terms of rotation. A sun-like star would form at something under about a day, about half a day period or so. And the color, of course, doesn't change, right? Because it's on the main sequence, but it spins down. The star spins down steadily, the sun, so that at the present age, it ends up over here. And this is, of course, a theory of how spin down occurs. But that's the basic idea. The rotation changes by a huge amount. So you could, in principle, use the rotation to tell the age, provided that the spin down is systematic. Systematic by mass, provided that all stars of the same mass spin down in the same way, and that there's a connection between stars of different masses. Okay? Here's a little aside, because I've sometimes gotten to the end of a talk and people have been like, why do stars spin down? Well, here's why. This was discovered not that long ago, Parker, 1958, okay? That the sun, the atmosphere of the sun is not static, it's dynamic. It's charged, the charged particles blowing away. In fact, the best way of describing it are equations that resemble a rocket exhaust, not of a static atmosphere. But they're charged particles blowing away. The sun also generates a magnetic field. And because these charged particles have to move in this magnetic field, they take away angular momentum as they go. So it's actually a significant amount of angular momentum, so that over a time scale of billions of years, gigayears, the sun spins down. That's what Parker wrote in this paper, in fact. But it was only known for the sun, right? And of course, it was discovered by satellites and so on. For stars, it was Olin Wilson who made the solar-stellar connection, a whole project to measure a whole bunch of sun-like stars and other cool stars. And then his protege, Andy Skumanich, who plotted this very famous diagram in a 72 paper. In fact, this is the only figure in that paper. Now this figure, one of the plots in this figure shows the average V sin I of stars in the Pleiades, the Hyades, and the sun. 3 data points. It's amazing how little information there actually is in this paper. I mean, one figure, 10 references, of which 5 are to Wilson, okay? And this plot. So it's a tremendous return on investment to have written this paper. So anyhow, that's what he said the spin down of stars looks like. This goes as a power law with age, that power law being t to the minus 1/2. So it goes down, the period or the v sin I changes as the age to the square root of the age. Now, v sin I is an ambiguous quantity, right? V sin I. For the Pleiades is the zero-age main sequence from models. The older one, the Sun, from Patterson's work, 4.5 billion years. The Hyades has some giants, so you can pass an isochrone through the giants, and therefore you get. And it's, you know, if you look carefully over here, they have the Hyades at 400 million years. We think it's slightly older, but that's just a detail. Honestly, whether you call it 400 or 600, it's the same number. All right, so it's approximately correct. But there's a bigger problem here, and that is that this is V sin I. So in order to get omega, the actual rotation rate of a star, you've got to know something about the radius of the star, and you have to know this inclination angle, which you don't know a priori. You know it for transiting systems, but you don't know it for these kinds of things. So there's an ambiguity over here. So people got interested in telling the rotation periods of stars instead, which gives you omega, of course. What is the result? What is known about the 90s? So the Pleiades were measured. The Pleiades and Alpha Per lay in this region. There were some very fast rotators. By the way, this one, these stars are rotating close to breakup. So that sort of tells us that when stars reach the zero-age main sequence, the majority of them are born with maximal angular momentum. You couldn't spin up a star any further. I mean, it's 5 times in a day. It's just crazy, okay? There are some slower stars in those clusters. And then by the time you get to the Hyades, you have this very clear sequence that goes like this, right? With this is the Sun, by the way, at 0.65, right? The Sun has a B minus V color of 0.65, it's somewhere here. So Sun-like star in the Hyades would have an 8-day period. Okay, that's what it looks like. And that actually I found fascinating. It was like, why is that? Because that has something new in there. That's telling you something that's actually beyond what Parker said. So Parker's idea was the 1,000,000-degree solar wind, but he didn't tell you how this wind changes as a function of mass. This thing gives you an idea of how the efficiencies change as a function of mass. My models were pretty bad at that time, and so my thesis supervisor suggested going and observing. Luckily, Yale owned a telescope at CTIO, and it's very similar to things over here. It's a wonderful place to observe. You should be going to the telescope all the time, whether people allow you or not. Just go and use the telescope. It's so much fun. You go there and you fill the nitrogen and you make your measurements, and the morning you just go to sleep, sleep in. So the things that were measured were open clusters. Here's a cluster, NGC 3532 in the southern hemisphere, an extremely rich one. This, of course, is the cluster. This is the galaxy behind. Okay, this is the disk of the galaxy, and those are the giants in the disk, and that's the cluster. So assuming you have friends in the department who do proper motions, they'll go and tell you the membership, or you can even just fish out those stars from here, or you just measure the variability of all stars, and you'll find that the stars in the cluster go up and down. The stars in the galaxy are typically faint, they're older, and they don't vary as much. The stars within the galaxy, that's what the light curves look like if you measure them for about a month. And if you plot them in this diagram with the color, with the period, rotation period versus the color, you see something very curious. You have this triangular distribution. That really confused me during my thesis days, until I realized that this feature over here is sort of similar to the Hyades. But who ordered that? What are those? So anyway, as part of my thesis, I made some models of very young stars starting at the birth line. They go down the Hayashi track, right? When stars are fully convective, they'll spin up. They become very fast rotators. So you should find them at the bottom over here. Then they go up the Hennier portion of the track where they are radiative, mostly radiative, and they end up on the zero-age main sequence. And so you can do all the details of these models and try to compare them with observations. And that's what the observations look like compared to the models. And it doesn't take a genius to figure out that those models don't come close to those observations. There's something very wrong, actually. In fact, it led me to a serious case of depression. But then they still hired me in Arizona, so at Lowell, and I promptly, it was one of these postdocs where I didn't have to do anything. And so I didn't do anything. I just went hiking. You go hiking in here, and then you come face to face with the rock. And you have to do things instinctively sometimes. You can't sort of follow. But many years later, I realized that the meaning is this. Like, here's this piece of very famous outcrop in Scotland called Sychar Point, okay? And you look at this thing, and this is very similar to some of the features you have around here. Look at this rock here, right? You can agree that this rock is roughly horizontal, correct? Right, this is sedimentary rock, right? Some river has eroded the rock and laid it down in layers. But what about this? Who ordered this? What has happened over here? This is also sedimentary rock, very clearly. But what is it doing tilted over like this? Okay? And the person who figured that out was actually Hutton. In fact, that's called Sychar Point after Hutton himself. And today we know that this rock is 430 million years old, okay? Okay? This rock is 370 million years old. That's Devonian. This is Ordovician. The entire Silurian is missing. The Silurian lives here. So a set of mountains. So the sedimentary rock was laid down. A set of mountains was created, like the Himalaya. They got crushed, turned sideways, eroded down in that 60 million years. And then another set of rock was laid down. So you look at this thing. This is a small vignette of what's happening. And this happens on a very vast scale in Grand Canyon. Right? All those rocks, the sedimentary rocks on top, and then at the 1.3 billion year boundary, actually, a huge thing happens. There's a transition to very much older rock. There's a great unconformity in Grand Canyon. Okay? But in there, it's a wonderful place. I mean, you'll make friends with people there, and you go down, you take a boat and go through these rapids. These are huge, by the way. These waves over here are like as high as the roof here. And you can go and sit over there and throw rocks down. And, or if you take a boat, you can park your boat on the other side of this thing and go hiking into the hills. It's hotter than hell. But why would you go hiking over here? The reason why you want to go there is collect some of this rock over here. This stuff, okay? And you can take a boatload of this rock back with you. This rock, you can see it's black, right? This is volcanic rock. There was volcanism over here. And with volcanic rocks, the clock is reset, right? When the rock solidifies, all the elements, the radioactive decay stuff, gets sealed in the rock, and you can measure its age. In fact, those are the Cardenas lavas, right? You see over there, and their age is 1.1 billion years old. And you realize then that that's what you have an isochrone over here. You have an isochrone. All the rock above it is younger. All the rock below it is older. That's what an open cluster does for you in astronomy. It separates younger and older stars. And you can explicate that using a series of open clusters. And so if you're in an observatory, you go and measure every open cluster you possibly can. It's dead boring stuff, but someone has to do it. So now, sorry, this diagram is very complicated. Let's just focus on one panel, okay? This is a color period diagram again. No, sorry, it's not a color period diagram. It's a period versus age diagram, okay? This is log age in gigayears. That's period on a log scale. All these things here are observations, okay? These boxes are open clusters, the Mount Wilson stars in these boxes, and those individual points are planet host stars, okay? That's what it is. Forget these panels. These are lower mass stars and higher mass stars, okay? So just concentrate on the middle panel. Now, look at this middle panel and see what the observations, what the theory is doing. The fast rotators, they begin fast. Stars are fast in the beginning. Why? Because they come down the zero-age main sequence and they come down the Hayashi track. As they come down the Hayashi track, they become very fast. Then the wind kicks in and then they spin down over time. So you can see what's going on. So that's what's happening. The models, they're sort of doing that, but they're actually all in the wrong place, right? You're much better off throwing the models away, even though you've devoted years to developing the models, and just drawing a set of lines over here, okay? These lines are the same. And what I want you to see is that the stars in this panel are between these two lines, okay? Between the central two lines. The lower mass stars are between the upper lines, and the higher mass stars are between the lower lines. The other thing to see is that these are planet host stars that I've plotted. They follow the same spin down as cluster stars. There is a universality in the process. But the fact that these are fast, those are slightly slower, and these are even slower, that tells you that the mass dependence is the same as you have noticed in open clusters. In fact, if you look at it's basically a projection of the data into different spaces, right? This is the PT space. You can also project it into the color period diagram. And if you do that, okay, and you make panels for each open cluster, T1, T2, T3, T4, what you see is this. The youngest clusters look like that. This was 20 years ago, so it looks very noisy. It's much better today. But here's what you see. You see stars slowly spinning down, right? Because these lines are going up, okay? And in fact, you can write down that relationship very, very simply by writing this down. Remember, V equals V of T whatever XYZ. That's the same thing. The period is a function of the age and the color, period. Stop. No other variables. How lucky are we? So you just invert that, okay? T equals T of P and B minus V. So in fact, Skumanich told us this was approximately square root of T. And then this function f of B minus V, which arises for reasons we don't know. You can simply invert this, right? You can fit that function using all these open clusters, and you can get the age of a cluster that way. So the interpretation is this. For the youngest clusters, they form this kind of function. Then G of T carries them upwards as stars spin down. There's a relationship between stars of a certain mass and stars of a slightly different mass. But this G of T carries them upwards, so they arrive at a different position. Okay? And that's what gyrochronology is, the study of how this spin down occurs. Of course, no one actually believes you until you do the error analysis. And so I worried about this for a while. In fact, I had sort of given up on this work because I thought, well, some student will do it for a PhD, but I had no other ideas and no one did it. So I went and did the error analysis. And it turns out that the uncertainty on the age that you derive this way is 2% times this complex expression, okay? And you put in the numbers for this thing, and you end up with numbers that are between 13 and 20%, okay? Now, that's kind of the uncertainty with which, any of us can guess the age of any other person. It's not a huge thing, right? I mean, in common parlance, it's not huge. But in astronomy, where you're talking in orders of magnitude, typically, it's actually something. It's better than nothing, in fact. And since no one found an error in my algebra, and they could see the algebra was correct, they're forced to accept it. So, and that has remained. But I have to tell you that I got into trouble for this paper. The director of the observatory, Bob Millis, says to me, Sydney, one paper in 3 years, no matter how fundamental, is not enough. You can't win always. Part 2. When I was a student, I would always take a nap in the middle of every class, every lecture. So if you feel like napping, this is the perfect time. All the details. So here are open clusters. So how do you work with open clusters? You have to find the members. That's the hard business with photometry, radial velocities, all kinds of stuff. This was part of Dario's Ph.D. thesis. Or you put fibers. You go to a 4-meter telescope and you put fibers. That's Sam Barden, who built the Hydra multi-object spectrograph. That's what it looks like. These are individual fibers. They sit on a magnetized thing, and they move around, so you can place them across a 1-degree field of view. Wonderful instrument from which we got a lot of data. What you get are spectra. They're not huge. These particular spectra are actually from the AIT, and they're little snippets around the calcium line, but it gives you an idea of what you can get, and you can measure the radial velocities of stars. That tells you not only the members of the cluster, it also gives you the binaries within the cluster, if you do it for sufficiently long. Another way you can get the membership, of course, is with proper motions, right? This is the motion in declination and RA and dec. And of course, stars in a cluster move together. You should probably look at that screen because the resolution is better, but anyhow. The rotation, of course, is measured with telescopes, time series stuff. And part of the big reason I'm in Germany is because I didn't have to go to the telescope too much after that, because this thing opens and closes by itself every night. So I can sit around over here and be eating dinner and doing whatever, and this thing keeps observing. So that's the genius who makes the telescopes work. And what you get, you can also do it with satellites, but everyone has access to these data. So essentially, they measure time series of stars. And what you get are, of course, light curves that look like this. These are stars in the open cluster M48. All of you know this, since you had the variability class with Santosh just before. And so the variability is typically of the order of a few hundredths of a magnitude. You can often read the rotation period by eye. You don't even have to do any fancy software, honestly. But of course, to convince your collaborators and get the paper accepted, you have to do all that jazz. Sometimes you even have to do MCMC and who knows what nonsense. The final result for those stars in this M48 cluster is a color period diagram that looks like this, right? The periods are scattered in this way. Remember the Hyades? A sun-like star in the Hyades had an 8-day period. This one, a sun-like star, has about a 6.5-day period. Okay, 6.5-day period. That simply tells you that this cluster is younger than the Hyades. Since the Hyades is 600 mega years old, this cluster is young. Turns out this one is about 450 mega years old. So you get the age of the cluster. There's a similarity. But if you look in detail, now let's look at a cluster that's very similar to the Pleiades, and this is what Dario did for his PhD thesis. That's what the color period diagram for a zero-age main sequence cluster looks like. A sun-like star has a period something like 3 days or so, 3.5 days. There's a very clear distribution. And actually, we're beginning to tell features within this distribution, like this thing over here. This is a very clear sequence. This thing is forming. We actually don't know what all these bumps and wiggles mean right now. So here's something for students actually to work on. Tell us what those bumps and wiggles are. We don't actually know. But from the point of view of telling ages, perhaps it doesn't matter. Right? Because if you look at a series of open clusters of the same age, you end up getting the same distribution, which is a positive thing. Of course, Einstein said insanity is doing the same thing over and over and expecting different results. But someone has to do it, so you do. The Kepler satellite allowed us to measure much older stars because the spots are much smaller for older stars. The wiggles are smaller. And so here's the cluster NGC 6811 that my friend Søren Meibom took the lead in analyzing. And here you can tell that unlike the Hyades, where the period of a sun-like star was 8 days, here a sun-like star is 10 days. This is older than the Hyades. In fact, this cluster is 1 billion years old. Those two stars, what are those? Those are exoplanet hosts. Those are Neptune-sized exoplanets, actually, in that cluster. And those were the stars with the best measured ages until they were found in other open clusters. The reason you know the ages of those planets, the reason why you know the ages is because they're members of that cluster by association. So no matter how you tell the age of that cluster, someone may say, oh, it's 1 billion years old. Another guy may say 1.1 billion. Okay, that's a detail you can fight over. It's basically 1 billion years old. And those planets are exactly that old. And you keep going further because you don't have anything better to do with your life. So you keep doing the same thing. And you measure NGC 6819. And you find out that their sun-like star is a period of 18 days. It's a significant jump, okay? This was a horrendously difficult cluster to observe, partly because the stars were very faint. And in order to do the membership, we had to get a lot of time on MMT to get the membership correct, and the binaries and nonsense. And finally, we measured M67 with the light curves that the mission provided in 2016. And what we found out was that a sun-like star finally had a period that was comparable to that of the sun. Look here. This cluster is 4 billion years old. We know that from other things. But the rotational distribution is reminiscent, of course, of the Hyades, but a lot higher. These periods were difficult to obtain because there were problems already with the satellite. This was the K2 thing. So the satellite, one of the gyros broke down, was doing strange stuff. Nevertheless, you could get the periods, and people actually didn't believe these results for a long time. I had Suzanne Igraine from Oxford like buttonhole me and say, we got different periods for the stars. I was like, okay, you got different periods for the stars, right? So publish it. So anyway, partly as a result of that, and because of the pandemic, which was a really bad time, but I got really bored and I started going to the office, and David started showing up in the office too. So we said, well, since we have time on our hands and there are only 2 of us here, why don't we do the same thing again? We worked on the central superstamp in M67, for which the mission hadn't provided light curves. And this is not something you would do if you have better things to do. But that's what you do. So that's what it looks like, the central superstamp. And what happened was in K2, it lost the gyro. So the stars would like go across from one pixel to another. So they're doing this dance, back and forth. And those of you who do photometry know that that this is miles. This has horrendous effects on your light curves. But it turns out that you can actually classify each point in certain ways that's excruciatingly laid out in the paper. So if you're really bored one day, you can go look at that. And you can do the corrections and find that the period of this particular star, for instance, ends up being about 28 days. I keep doing it for other stars. And eventually you end up with 47 of them. Okay, 47 stars. That's worth spending a little time on. And the period distribution that you get is this thing in blue. Weird, huh? Well, who ordered this? This bump over here. But it turns out that the stars we had measured earlier were right there. So we knew that the stars we had measured earlier were correct because the new measurements lay right on top of that. Furthermore, there were other measurements made from Hawaii, from a ground-based telescope, of stars in M67 that ended up being here. Okay? So we knew that this thing was also correct, and that is the empirical distribution of how stars rotate at 4 gigayears. If you want other colors, they're in there. The final result for stars over 1 billion years in the color period diagram is this: 1 billion years over here in green, 2.5 billion years over here in red, and 4 billion years over here in blue. So you can simply interpolate. Provide you get yourself a star and you say somewhere it's over there. Well, it depends on your interpolation program, but you certainly know it's between 2.5 and 1 billion years just by putting it in this diagram. So whether it's a planet host star or not. A final thing, if I may have. The problem is we've worked only in open clusters so far, but we want to get to field stars. And how do you do that? It's like, whenever there's a giant problem in mythology, the gods, say, okay, we created this mess, but now we're going to try and solve this problem. And the problem is going to be solved by a person who's both man and God. Okay? And the Germans call such a person Siegfried, for instance, and so on. So these wide binaries are one of these very curious objects because they're the smallest open clusters, right? The smallest open clusters, and yet they're not found in open clusters. So this weird object that's both a cluster star and not a cluster star, it's a field star. So they actually connect clusters and field stars. And this guy, Karim El-Badri, published a ton of them. And so we worked on those stars in the pandemic. And this is the distribution on the color period diagram for those stars. It looks a little messy over here. And the reason why it looks messy is because there are these open symbols over there that connect to evolved objects, giants, and so on. You can clean those up, okay? And then you have to try and interpret that mess. And it turns out it's not a good idea to compare those with models because the models are way off the mark. So the way we came up with is to compare them directly to the open clusters that had been measured. So you take all the open clusters and you plot them in this diagram with different colors. You plot the sequences of those open clusters. You layer them, as in geology, in this layering of the color period diagram. You call it a stratification. And then you ask the following question. Let's take a wide binary where one component is there and ask where the other component lies. Is the other component going to lie in a different layer, or is it going to lie in the same layer? It's like using an index fossil in geology. And it turns out they lie in exactly the same layer. So the youngest wide binaries are there in those layers, the older ones successively. So each set of wide binaries can be associated with the corresponding open cluster, and the pattern is the same in the wide binaries that it is in open clusters. In fact, if you Organize the white binaries. That's how they look like. The layering is identical. And it should remind you again of the Grand Canyon and the layering in there, except that in here, the oldest rocks are at the bottom, the youngest rocks are at the top. It's just slightly inverted. In fact, if you do the interpolation for the ages, and you plot the age of one component of the white binary versus the age of the other component, you end up with something that looks like this. This is the line of equality. The red stars are the ones that are not pathological. The blue stars are pathological in ways that are described in the paper, triples and so on. But if you look at this, the standard deviation of this sample is 0.3 gigayears. So for a star that's about 3 gigayears old, you're getting a 10% age. But more than that, you're getting a consistent age for both components of that white binary. That's the end. So Wendell will be happy. It's possible. So the summary is that it's possible to derive the age of a cool star. Gyrochronology is usable for cool dwarfs to at least solar age. The underlying principles are fundamentally simple, but detailed work is necessary, time-consuming, and requires extensive resources. We've measured both cluster and certain field stars, which are, of course, the ultimate target, and robustly connected the two kinds of stars using white binaries. The ages of planets follow and could enable an understanding of how planets evolve, especially if this works out with the Plato satellite that's going to be launched in a couple of years. Extensive applications are envisaged, Plato, Haydn, etc., enabling an understanding of astronomical chronologies, I should add, of cool stars in the galaxy. I'll stop there. Thank you.
Yeah. So thanks, Sydney, for this wonderful talk connecting geology to astrophysics. Yeah, I was happy to listen to the talk. So no. So any questions, comments? Yeah.
What's your explanation for this hump in the color distribution? So there is a hump there. So
You know, I could give you some bogus answer, but I won't because we don't know. Federico Spada worked with me for a while. We wrestled with this problem for a while. He published a paper with Alessandro Lanzafame that says that it tells us that there is a coupling between the interior and the exterior of the star. That coupling occurs just once, but it proceeds in a certain mass-dependent way such that angular momentum is resurfaced from the inside to the outside of the star, which is what allows you to get those fast rotators. Those models haven't placed the bump in the correct place so far. So that's a proposal. It's a possible explanation, but my personal feeling is it's a lot more complicated than that. And I personally have the prejudice that this has to do with magnetic fields on stars and with a change of magnetic configuration. Because there are certain regions where stars actually spin down very, very little, others where they spin down a lot. And so we haven't actually connected all these things together with the magnetic geometries of stars. Even in the case of the sun, you can tell from Parker Solar Probe and other missions, perhaps even Aditya, that the solar wind isn't exactly regular. But of course, it's just the sun at one time. If we were to measure other stars, or from Maunder minimum and various other things, there are variations. These are slow processes, long continued, in Hutton's words. So there are complexities that we don't quite know at the present time.
mostly these bombs for like late time stars.
That's right.
How do you take care of the closed binary systems, whether it's a single star rotation of the closed binary system because the Tadley log trying to spin up the companion?
Oh, yes. Oh, there's a big mess. As Joe Casanelli said, to Bob Matthew, a binary is a system with one star too many. So mostly we get rid of binaries, but in fact, we found out that the closed binaries, there's obviously been angular momentum transfer between the two components, and there's been transfer. But it turns out if the binaries are wide enough away, and they don't have to be that far away, like a 10-day period is fine, then both components are actually in the correct place. So that's a very curious thing. So we have stars that you can say, oh, they're on the equal mass binary sequence, and the rotation is exactly known. But you're
Wide
completely
binary-
right. There are systems where
Yeah.
there's a
Binary
lot
is
of,
fine. They are far away, then period will get too high,
Right.
too large.
but even photometric binaries, you can, most of them are normal, but some are highly abnormal. We haven't yet mapped this thing in, you'd have to know the orbits of all these stars and then map them in eccentricity and orbital separation space and see where things go haywire.
It appears like these ages doesn't matter on the chemical composition of a star. Like in different clusters, you are getting similar sequence. So this open cluster is like starting at a different initial mass function is going to the same sequence over and over. So what could be the reason for that?
Okay, there are two parts to your question. One part is the composition. The composition part, actually, most open clusters that we've studied to date, they're in the solar vicinity. They're within 500 parsecs. Sometimes we've gone further. With Kepler, we've gone to little over a kiloparsec. They tend to be of roughly solar metallicity, so we don't know. However, the Hyades is slightly metal rich, and so we're slowly beginning to suss out these metallicity differences. In the case of the white binaries, we don't know their metallicities too well, but we know that there's a range of metallicities. They're around solar. We haven't triaged them into, we could just triage them into solar metallicity, supersolar, and subsolar, and try to see if there are differences. That will come with time. The other thing is, you asked about the convergence of rotation periods onto the sequence. That's a different issue. And that happens because the rate of spin down of stars, dj dt, where j is the angular momentum, that goes as omega cubed. J is I omega, I is the moment of inertia, right? And so you find that the rate of change of the angular momentum, right, if I is constant, the rate of change of omega goes as roughly as omega cubed. That's highly convergent. And there's a reason why it's a cube, because that tends to follow from linear dynamics, where the magnetic field is roughly proportional to omega. So it's just an empirical observation from stars that this is convergent. And that's what helps all this stuff to occur, the ages. Because if that didn't happen, it would be all chaotic.
So you see, these cool stars also show the differential rotation.
That's correct.
So what is the impact of this differential rotation on your age?
Yeah, Santosh asked a difficult question. So you see, in the case of the sun, the equator rotates with a period of about 25 days, where the poles rotate at a period of 31 days. So what really saves us is the fact that the sunspots are located at mid-latitudes, and they don't like to go away from there. So really what I'm quoting is the average rotation period for the sun, which is about 26 days. We assume that other stars like the sun also have similar periods, but if the spots were to be located in a different region, we'd likely be systematically off. In the case of differential rotation, the uncertainty seems to be about 10%, right? Which is something, but it's not a huge amount in this thing where the rotation changes by 2 orders of magnitude. So to a certain extent, it contributes to the uncertainty in the rotational ages, but it's not a game changer. Does that answer the
Yeah,
question?
so one more question. So why do not think that this gyrochronology is applied for the hot stars? Even they have the rotation period, if they have some rotation period, and this technique can be applied. Why only for these A and particularly on cool stars? And what is the range of the stars where this technique is applied?
This technique is only applicable to stars with surface convection zones. And
Okay.
those end up being late F, G, K, and M. For more massive stars, they have radiative outer regions. So he's asking it for the benefit of the students, I know full well. Those stars have radiative outer regions, and they actually don't spin down much. The spin down is likely of a different origin. It's not related to the magnetic fields per se. But that's yet other work to be done. If you go back to an old paper, Kraft 1976, you'll see from the V sin I measurements that the V sin I's of hot stars are all very, very high. And then there's a sudden break called the Kraft break, at which point you get to the cool stars. So that's what we see.
Thank you for such a nice infotainment, sir. But you just answered my question.
Okay, well, then even better. Even better.
Thank you.
Other question on students? There are many things you can ask about the different places you visited also. So many places.
Yeah, maybe I can ask one for also the membership of particularly this sunlight stars, which are old age clusters. It's challenging. So how do you handle? I mean, you always go to spectral type because you showed also the fiber fed instrument. So you went there for spectra, or you Dr. Wilson could please put light on this.
Yes. When I was a student, we started with photometry of open clusters. And you hope that the cluster stars, that you can see a cluster sequence when you form the diagram, the column magnitude diagram, and that the cluster sequence is slightly separated from the field. So then you can tell the members photometrically. There's, of course, a binary sequence on top of that, and that makes things complicated. I was fortunate to be in the Yale astronomy department, where there was a proper motion group, the Yale Southern Proper Motion Group, and they had plates from 100 years ago, from El Leoncito in Argentina. And so then you request them, and they go and take a next set of plates of your cluster, and then look at the motion in 100 years. Now, of course, Gaia has changed a lot of that. So a lot of membership has been helped by Gaia to these kinds of stars, 18th magnitude. But actually, some of them, even Gaia doesn't help us, because we can go fainter. Photometrically, you can go fainter. The other thing is, since I was a theorist, they gave me a telescope that no one used, a 1 meter telescope, which people didn't, everyone wants the biggest, fanciest thing. They kind of leave the other stuff, which is amazing to me. So, but it turns out that the 1 meter telescope is the best. Why? Because you can get spectra for the same stars with a 3.5 meter telescope. So you do the photometry with the 1 meter telescope, you do the spectra with a 3.5 meter telescope, which was WIN in my case. And because it had many fibers, I could do open clusters over a 1 degree field of view. You could get the membership. So it's multiple things. Yes, we have also field star spectra that when we said, oh, okay, we put the fiber in the wrong place. You can't guess, you don't know beforehand. So you just throw those out. Yes,
But
that's correct.
is there any other method like observation of X-ray or gamma ray
Oh,
or
yes.
radio observation to find out the ages? And there is any correlation between the optical observation?
Yeah. That's a good question. Rotation is just one aspect of the activity of stars, of cool stars. You also see the activity in calcium HK, in the calcium infrared triplet, in H alpha, and various other bands. And you certainly find it in X-rays. And so we also have X-ray observations of certain open clusters, and they follow a typical pattern. There's a dependence both on the color and the rotation periods of stars, and perhaps additional things. That's under active investigation right now. It's been investigated before, but in the past, people didn't have rotation periods for many of the cluster stars. So they had the X-rays, but no way to interpret. And it turns out that you need the rotation periods to do that, in addition to knowing which ones are the binaries. Because the binaries, of course, very bright in X-rays.
Thank you.
You are saying like the cluster age, and then you have star age. So how do you determine the cluster age? Because you basically determining the age of the stars. So can you just describe the age of the cluster?
The age of the cluster is typically determined by an isochrone. Ideally, you take all the clusters and pass the same kind of isochrone, classical isochrone through, and you say, okay, here's what the isochrone ages do. Now, then you go to the rotation rates of stars, and you say, at this isochrone age, the rotation is doing X, Y, Z. Once you know the pattern of how rotation changes, then you can look at the in-between stars and say, oh, okay, here's a cluster for which we don't yet know an isochrone age, but the rotation is between this and that, and therefore it's likely 450 megayears old and not, 500. So that's the logic of the process. I have another, actually, I realize many of you are busy, so I can let you go. But I have another small presentation for the students that's picture heavy, shall we say. And they can, buttonhole me tonight. Apparently I've been invited to this place, so you can find me, at the party, and so you have a meeting, exactly. So why don't you go on, and if until they get bored, these front lights, if someone could take off.
So I'd like to let you know that the name Sydneybarnes, this is a very different name, right? He is born and brought up in India, and he is a US citizen, and he is primarily working in Germany. So he is connecting three continents also, like geology to that. And the name Sydneybarnes, I mean, whoever is a great fan of cricket, they might know Sydneybarnes was a player, right? Bowler, like.
Bowler, Australian.
Very much fan of cricket, so the name Sydneybarnes of that. Okay.
Thank you, Suendu. So I thought I would just give a little. Oh, can we stop stop the share on the? I think I want to end the formal part of this because there's some personal stuff here. So. Okay, I'll answer some questions that that some of you probably thought of but didn't want to, felt too embarrassed to ask me. So, oh, why is it not playing? Can I? Okay, great. Thank you. Okay, so the questions you didn't want to ask me. Where am I from? Well, really, my family is scattered around this part of India, around the town of Udupi, which is a temple town. In fact, my dad comes from this little village called Barkur. Our family property is right near this Panchalingeshwara temple, actually, over there.